So to begin with, we'll be talking about distance and intensity. If you go very, very far away from a bright object, it looks less bright. That's because at the point at which you're looking at it very far away, the wave is less intense than when you're much closer to it. So we're going to examine just how that works. Now, as a wave travels, it always carries the same amount of energy. That's the conservation of energy. We can't destroy energy or create energy out of nothing. But waves do spread out as they travel. If we're looking at a 3D wave like light, it will spread out in all directions. Up, down, left, right, forward, backwards. So this means that the energy that they're carrying is also spreading out with the wave, once again, in all three dimensions. We can imagine that for a wave that's only two-dimensional, like a ripple on a pond, or a wave that's one-dimensional, like a wave in a spring, then it'll spread out in only 1 or 2 dimensions and not 3, like a light wave. Now, the further away we are from the source, the more the wave is going to be spread out before it arrives. If something is spreading out constantly and it's not reflecting or bouncing off any obstacles, then it will, as it spreads out, it will just keep getting weaker and weaker. One way that we can increase the amount of energy that we receive from a wave is by increasing the size of the receiver. Binoculars are a good example of this. The human eye is not huge, as you know, but if we look at, for example, these binoculars, they have a lens to pick up light which is very, very large compared to our own eye. And the way that the binoculars are constructed funnels all the energy from the light it receives into the eye, so that we can see a further distance away without it being much dimmer. The total power output of a source of waves at a given distance from the source is given by multiplying the intensity at that distance by the area of the sphere at that distance. We know from the studies that we've just made that the energy from a three-dimensional point source will spread out in a sphere. So we can see that if we take the intensity, that is, the power going through the sphere per area, and we multiply it by that whole area, then we'll get the power. That is to say, intensity is power over area, and we're multiplying this power over area by the entire area. So if a light bulb has an intensity of 6 watts per square meter at 2 meters from the bulb, what is its total power input? What we need to do is find the area of this sphere and multiply it by this intensity. So what's the area going to be? I hope you can remember your geometry equations. The area of the sphere is of course going to be 4 pi r squared. Our intensity is 6 watts per square meter. Our radius is 2 meters. So our P tot, that is total power, will be 6 times 4 pi 2 squared. That is 301.6 watts. So we've taken the area of a sphere in meters squared and multiplied it by watts per square meter, and the meters squared have cancelled out and produced the watt unit. Remember that we can do algebra for units just as easily as algebra for numbers. What is the intensity and total power output at a distance of 4 meters? So first we need to see how the intensity will change. We're doubling our distance, which means that the intensity will change by a factor of 1/4. If we double our distance, we become 4 times as dim. So our new intensity is going to be 6 over 2 squared, or 1.5 watts per square meter. Once again, we can use this equation to figure out the total power emitted. But in this case, our radius of the circle isn't 2 squared, it's 4 squared. And that'll give us 1.5 times 4 pi 4 squared, which means that the total power emitted from the source is 301.6 watts, which, as we should expect, will be exactly the same as if we're standing 2 meters from the light bulb. This is because no matter how big the sphere is, we should always get the same amount of energy passing through it. The thing is, because the sphere is bigger, the amount of energy going through a particular part of that sphere will be smaller as the sphere gets bigger and bigger.